nothing beats. In this video, we're going to look at a couple more examples of how to apply the process of implicit differentiation. So it's time to go. Let's go. So like I said, we're going to do some implicit differentiation, and we're going to look at two examples here in which we're asked to find dy dx, slope of some curve at some point xy, for each of the following relations. First relation here is sine of x minus cosine of y is equal to 1. All right, so first thing to take note of is that up here, when someone asks you to find dy dx, obviously that is the slope of the curve that we're looking for, the instantaneous rate of change at a point. However, remember that the x in the denominator of that expression denotes the independent variable with which variable we differentiate with respect to. Treat x as the input, and then the y, of course, says that's the dependent variable. So that is important because when we do the process of implicit differentiation to an equation like we see in part A here, it matters. Now remember the first step. First step is always going to be differentiate both sides with respect to the input variable, that being x here. So I'm going to take d dx of sine of x minus cosine of y, and that's going to be the same as d dx of just the constant 1. Now, when we go through our differentiation process, of course, the derivative with respect to x of sine of x is just cosine of x, right? And then minus the derivative with respect to x of cosine of y. And the derivative with respect to x of 1 is just 0. Now comes the step in which we have to differentiate cosine of y with respect to x. And here's that implicit step really, is that remember that y is the dependent variable here, right? So y is the output variable, x is the input variable. So you should think that y somehow, one way or another, depends on x, right? Even though we can't necessarily isolate that y as a function of x explicitly. And that's that chain rule. So you really think of this equation is the same as cosine x minus the derivative with respect to x of cosine of some function that we don't know. And hence, when we do that differentiation step for the cosine of y, we got to apply the chain rule. And what do we get? We get cosine x minus derivative with respect to x of the inner function, y, and then the derivative of the cosine function, the outer function, is a negative sine function, and then we leave the y alone. And that all equals 0. And thus, the result is that we get cosine of x minus a minus, or really plus, a sine of y times dy dx is all equal to 0. And thus, once we've done the differentiation process, the next step is to solve for dy dx, and that's exactly what we'll do. I'll subtract the cosine of x on both sides to leave me with sine of y times dy dx is equal to negative cosine of x, and then even further, divide both sides by sine of y. What do we get? Dy dx is equal to negative cosine of x over the sine of y. And there you have it. We found dy dx for the equation sine of x minus cosine of y is equal to 1 by using the process of implicit differentiation. Now, just to get a visual here, here's the graph of sine of x minus cosine of y equals to 1. So if we could find a point on this graph, say right there and say, what's the slope at that corresponding point? Then we would just plug the coordinates x comma y at that point into our formula above, and we would get the corresponding slope of the tangent line there. That's the whole point of this. All right, we got one more example to look at. And in this case, this time we have that the sine of x divided by y is equal to x minus y. So again, we're asked to find dy dx. And that means we're going to differentiate both sides of this equation with respect to x. So d dx of sine of x divided by y now is equal to d dx of x minus y. So you notice in this situation, we have expressions involving both x and y on both sides of the equation. And again, we're treating x as the input variable and y as the output variable. So anytime we're doing a derivative involving the variable y, we have to remember to apply the chain rule. And so on the left-hand side, we notice, you think of this sine function here, sine of x over y, it's really sine of some function, right? It's like, okay, well, it's really sine of x over like a function of x, because since y depends on x one way or another. And so you can kind of think of it as sine of some function in general. I don't know, call it k of x. And so when I differentiate that left-hand side, I have to apply the chain rule with the inner function k prime of x, and then, of course, the derivative of the sine function with respect to the inner function. So what's that give us? It gives us the following step. All right, left-hand side, derivative of sine over x over y. The derivative of the inner function, say d dx of the inner function, x divided by y, times the derivative of the outer function, which is sine here, which gives us cosine, of the inner function, x over y. Right-hand side, derivative of x with respect to x is just 1. And then minus the derivative of y with respect to x, well, that's just the derivative of y with respect to x. That's what we're after, right? So that's that step. So what do we still have to do here? Well, there's this derivative of x divided by y, keeping in mind, again, y is the output variable. So that's a quotient of functions. So we actually have to apply the quotient rule there. Let's do that. Let's apply the quotient rule. So we're going to get, all right, the denominator y times the derivative with respect to x of the numerator x minus the numerator x times the derivative with respect to x of the denominator y. That's that numerator part. All of that is times cosine of x over y. But don't forget, we still have to do this and take a denominator of the denominator, y here, being squared. And all that is 1 minus dy dx. So we're getting closer. Let's differentiate that bracket step. We got y times the derivative of x with respect to x. That's just 1, right? So we get y times 1 is y. Minus, well, the derivative of y with respect to x, we don't know what it is. That's what we're trying to find. So we get x times the derivative of y with respect to x all over y squared times the cosine of x over y is equal to 1 minus dy dx. So we've done our differentiation step. And now the process is we got to isolate dy dx using our algebra techniques. So let's do that. First thing I'll do is notice that the left-hand side has that common denominator with y in it. So I'm just going to go ahead and multiply both sides by the y squared. So what do we get? If I do that, multiply both sides by y squared here. Let me just make some room. Then I get, the next step is that, well, left-hand side will be y minus x dy dx. All of that times cosine of x divided by y. And I'm going to go ahead and distribute the y squared on the right-hand side and get y squared minus y squared dy dx. And now on the left-hand side, we have some terms, right? We have a y and an x dy dx with a minus sign in between them, all multiplied by the cosine of x over y. The goal is to get dy dx by itself. So what we should do is distribute the cosine of x over y and get y cosine x over y minus x cosine x over y times dy dx is all equal to y squared minus y squared dy dx. We're getting closer here. So you can see at this step, we can get our dy dx terms on one side of the equation. Doesn't matter which side, but what I'll do is I'll take the term on the right side of the equation, the negative y squared dy dx, and I'll add that to both sides. And then simultaneously, I'll subtract the y cosine of x over y. So I'm going to subtract y cosine x over y on both sides of the equation here. But then what I'm also going to do is add a y squared dy dx to both sides, like so. And what that does is going to give all my dy dx terms on one side and all the non-dy dx terms on the other side. So what's left on the left-hand side? We have a positive y squared dy dx from the red term minus an x cosine of x over y dy dx as so. Right-hand side, we're going to have still the y squared term, and then we're also going to have the minus the cosine of x over y term. And now we're really, really close here. Notice the left-hand side has a common factor of dy dx. So if I take that out of both terms, I'll be left with a y squared minus x cosine of x over y all times dy dx. And that all, of course, equals y squared minus y times the cosine of x divided by y. And then finally, what we can do, and you can see the graph below, right? Sneak peek, is divide both sides by the y squared minus x cosine of x over y, the coefficient, if you will, of the dy dx, and finally obtain that the derivative of y with respect to x here in this situation is y squared minus y cosine x divided by y, all divided by y squared minus x cosine x divided by y. So that one was pretty involved. We had the quotient rule involved and terms on both sides of the equation, both with x's and y's. So you can see these things can get involved, if you will, but it is what it is. There's our slope at any given xy, given the original equation. Sine of x divided by y is x minus y. Now look at the complexity of this graph. Here is the graph of the relation that we started with. And so you think now, okay, we found our slope. Very difficult to figure out where we are. But if we were able to figure out where we are, maybe on this nice swoosh up here, draw a tangent line, then at that point, if we knew what that x comma y was, plug that x comma y into that formula we just found, and what would we obtain? We would obtain the slope of the tangent line as drawn in the picture below, wherever it might be and wherever it might exist. And there you have it. A couple of examples of implicit differentiation. Implicit differentiation, combining that with the chain rule, of course, because that's very much involved here in this process. Take those two ideas, and it allows us to come up with the derivatives of all of the other functions that we have not looked at thus far. So we'll do that in the future videos. Keep following along in this calculus discussion to learn more about calculus. And that's the end of the video. So you know what? It's Matter Beats, and I'm gone.